So we're trying to show that if you have two subspaces, that when we take the intersection of those two subspaces, that the intersection is also going to be a subspace. And so we need to show both that the intersection is closed under addition and also that the intersection is closed under scalar multiplication. Let's do the scalar multiplication part. So for number 2. We're trying to justify something that sounds like for all. Right? So for all b in the intersection w intersect z, and for all constants c, all scalars, that we have c multiplied by b is an element of w intersect z. So if I'm trying to, in my proof, write out something that begins with a for all. So we never say for all in the purposes of writing a proof. So let's just start my proof here. We're going to try to follow that 5-step proof scaffolding that we've been talking about this semester. So we wish to show that w intersect z is closed under scalar multiplication. And so what I would want to do here is set the context. So I have to instantiate, that's the fancy word that computer scientists might identify with, but it really means that we can't say for all as part of a proof. We have to be concrete and say, here is a b, here is a c. Now, not concrete in the sense of making those things specific vectors, because we don't even know what kinds of elements are in this vector space. So we're not going to be able to do anything other than give them names and say what properties that they have. And so in a proof, the words for all turn into the words let b in the intersection be chosen arbitrarily. So in other words, we're saying that the universe gets to come along and the hand of fate picks out a b from my w intersect z. And that takes care of this for all. And then the next for all, we'll just sort of bundle in with this one. So let's let b in the intersection and c, a real number, both be chosen arbitrarily. And now comes the statement of the burden of proof. We need to show that c multiplied by b belongs to the intersection. Whoops, make that a vector b. There we go. All right, so now we know what the burden of proof is, like how we're going to establish the result that we're trying to establish. So how do we establish it? Like, what do we know about c times b, if anything? In a way, the statement on this line here shifts the burden of proof a little bit, and it lets us use the definition of intersection. So the definition of intersection is going to be important as part of this proof. So let's unpack this statement. Just one more line here to sort of refine our burden of proof. In other words, what? What does it mean to belong to the intersection of w with z? So once we have split apart this assertion that c times b belongs to the intersection into these two individual assertions that it's a common element to w and z, now we're in good shape, because to show that c times b belongs to w, we just have to remember that w is a subspace by assumption, right? And b, because b belongs to the intersection of w with c, so in particular, we know that b belongs to w, right? So b is an element of the subspace w. And therefore, since w is by assumption a subspace, I'll say this is by definition of intersection. So, by definition of subspace, we know that c times b. Let's back up a step. By definition of subspace, w is closed under scalar multiplication. That's part of the definition of subspace, after all, right? Therefore, c times b belongs to w. Right? which was one of the things that we needed to know. What's good for the W is good for the Z, right? Because the only difference between them is their name. Their properties are all the same. And the fact that B belongs to the intersection means that not only does B belong to W by definition of intersection, B also belongs to Z by definition of intersection. And since we assumed that Z was a subspace, that means it's closed under scalar multiplication, and therefore C times B belongs to Z. So there are all of our warranted implications as a part of this argument. So therefore, by definition of intersection, C times B belongs to the W intersect Z. And that concludes that portion of the proof. So this is sort of a template for something you can probably see from this kind of reasoning, how you might be able to do the same kind of thing but with addition instead of with scalar multiplication. I think probably the key step, like I said, is the one that happened on this line, where we take apart the intersection, W intersect Z, using definition of intersection, to realize that we actually need to prove these two things. And then to prove those two things, we just had to appeal to the definition of subspace, because we assumed that W and Z were subspaces.